Everyone is here. Now let's begin our today's class. First, I'd like you to check your answers. For those who are not able to come here, you should also do the exercise by your own and check the answers. So, among the four students, only the Benedict didn't finish the job. So next time you need to finish it all. Okay, it's very important to finish the exercises. So let's first check our exercise 1. The exercise 1 is the first number is 10 to write the 5 numbers according to our 5 series. It's very easy if you check the table 1-1. If you look at the table 1-1, and you can find the answers. For the table 1-1, it starts with 1, not 10. But you just multiply the preferred values by 10, you will get the answers. So you guys need to check if you got the right answer, okay? It's easy. Now let's look at the exercise 2. The exercise 2 is to write the 5 numbers according to 10/3. There are some printing mistake on our textbook. It should be changed to 10/3. So it's also, you can find an answer according to the table 1-1. It's just you can look at the 10 series, and every 3 preferred values we choose 1 out, and you will get the answers. The answer is 100, 200, 400, 800, and 1600. Okay, 1000 and 600. That's the exercise 2. So for exercise 3, it's the first number is 1 to write the 5 numbers according to these 4 series. So for 10, you can just find the answers according to the table. You can directly get the answer. So that you need to check if you get the right answers. Okay. Then for the second series, it's the 10/2. Yeah. It means every two preferred values in the 10 series, you pick 1 out. So we got the 1 and the 1.6 and the 2.5 and the 4 and the 6.3 and the 10. So that's the 10/2. Then for the 20/3 series, we first find the preferred values in 20 series, and for every 3 preferred values, we pick 1 out. Then we got the answers like this. Okay, just you can find the answers according to our table. And for 5/3 series, that means we first find the 5 series, and for every 3 words, for every 3 preferred values, we pick 1 out. That's the 1, 4, 16. It's not 16/4, it's 16/3, and 215, and 1000. Okay, that's the answer for our last homework. So you need to know how to find the answers according to the table 1-1. Okay, that's the review. So now let's begin our new classes. Today we are going to learn the chapter 2. Chapter 2 is about the limits and fees. We are going to learn the first 2 sections of this chapter. The first section is the basic terms and the definitions, and the second section is the standard of limits and fees. So this chapter is really important. I think there are at least in your exams, what do you say?
Two questions.
Two questions, yeah, at least two questions in your exams. So you need to really learn it by heart. Okay. There are many new terms you first learn. You need to know what it means and know the basic calculations. There are many calculations in this in today's lesson. You need to learn it very carefully.
What is more important? Same.
So you're asking why it is important, right? Because when we connect different work pieces, they are connected. They are the tightness is different. It can be it can be rotated relative to each other. There are clearance, and sometimes we want to connect very tight, and that's the they have the interference. So sometimes we just in different conditions we want the workpiece connected together with different tightness. So how the tightness determined? It's determined by the feet. And when we manufacture the products, we set the limits for it. The upper limit and the lower limit. Yeah, that's very important. Okay, so let's move on. First, we know the basic terms and the definitions about limits and the feet. First, I'd like to introduce the terms of features. We talk about the features very often, but in this course, feature is referred to the physical portion of a part, such as a point, a line, or a surface. So in this graph, sphere, coin, plane, cylinder are all features. They are all features, and as we can see, they are really exist for this workpiece. They are really exist. They are the we can say it's the integral feature. They are categorized into the integral feature. And we also can here we have this the center point of this sphere and the center line of these workpieces. They are not really existed, but they are the center line and the center point. We call this. So the center point and the axis are also features. They are not called the integral feature. They are called the derived feature. So we will talk about feature a lot. So when you see the word feature, you should know what it refers to. We will not go very deep into about feature, but you should know we have some terms about the feature. The first one is the nominal integral feature. So when we draw a part like this one, cylinder, so the surface, the integral surface is called the nominal integral features, and its center line is called the nominal derived feature. Why? Because the nominal means the ideal, perfect form. When we draw it, it's in the perfect form. So the perfect form is related with the word nominal. And when we make the workpiece according to the drawing, we can see it's not ideal. It's the real one. For the real one, we got the real feature. It's the real feature. And according to the workpiece, we can draw its extracted integral feature and the extracted derived feature. And based on the extracted integral feature and the derived feature, we can get the associated integral feature and associated derived feature. It's just to give you an impression. You don't have to remember all this, but when we talk about the feature, you know it's referred to center line or the integral surface. It's okay. You know, feature is referred to name. That's all. It's not the key point. So now let's move on to the terms of shaft and hole. As we can see, shaft and hole is very common in mechanical engineering. Sometimes we got a real shaft, it's a shaft, and we got a hole here, here. And these two parts can be said the most common parts in mechanical engineering. And here we give the definition about the shaft and holes. In mechanical engineering, all machine consists of different workpieces, like this one. It's a component in gearbox, and they had many components like bearings and gears and shaft and bearings, and it's got this key. The workpieces should be fitted together to ensure the machine work according predetermined. And from fit point, the parts fit together can be looked at as two faces, and we just start with the two faces. Yeah, when fit together, they always can be seen as the two faces. They are fit together. And we use the shaft and the hole to present the two faces fitted together. For shaft, it refers to the external feature of a workpiece, including which are not cylindric. For example, the key workpieces. So when we say a shaft, it does not have to be a cylinder. It can also be like this one. This one. It's a key workpiece. It's a key workpiece. It's also seen as a shaft. Why? Because when it connected with this slot, the external feature of this workpiece is fit with this slot. It's the external feature. So in the same way, the hole refers to the internal feature of a workpiece, including those workpieces that are cylindric. So for example, this slot, it is also termed as a hole, So the shaft and the hole terms extend the relative standards application range. They can be used to grooves and or slots, which is common feature in machine workpieces. So let's look at these components in this green component workpiece. So what do you think? It's a hole or it's a shaft? It's a shaft. It's a hole. Why it's a hole? Because the shaft its internal feature fit with the shaft, right? So you think it's a hole, right? But we should also see that it can.
Cylindric. Shaft is not cylindric.
Pardon?
No, see, this is not cylindric. This is cylindric, but shaft is actually cylindric.
This one I think it's cylindric.
Yes,
it's
cylindric, but shaft is not.
Which one is not?
Shaft.
The shaft. In most cases, not both of them are shaft, but both of them are cylindric. Both the shaft and the hole are cylindric, but for some cases they are not. Such as the key workpiece. The key workpiece, it can also be seen as a shaft, and the slot, well, to mount the key workpiece, it can be seen as the hole. But I'm talking about this green workpiece. So we can see the green workpiece has two features: the external feature and the integral feature, right? Integral feature and the internal feature. So for this internal feature, it's a hole, right? For the external feature, it's a shaft. So it is both a shaft cavity and it's both a shaft and a hole. Also for the bearing, yeah, it's the same, right? The bearing has the external feature and also has the internal feature. So for the internal feature, it's a hole, right? The shaft, because it's connected with the shaft, this shaft, and for the external feature, it can be seen as a shaft because the bearing is always mounted here, mounted somewhere, and when it's mounted somewhere, it can be seen as a shaft. Okay, so we introduced the term of shaft and hole. They are not always cylindrical. Sometimes it can be a workpiece like this. It's a key. The key is also a shaft. The slot is also can be seen as a hole. So it's a general term of shaft and hole. So let's see another example. Okay. For these workpieces, let's see. For this blue one, the blue one is definitely is a shaft. It's very easy and it's a cylindrical. It's a cylindrical. So let's see about this the yellow one.
It's
It's a hole, right?
Yeah.
Why? Because it connects with the shaft. The hole and the shaft is always they are fit together. So, but let's see this one. It's definitely a hole, but is it also a shaft?
It's just shaft and inside
Yeah.
internal.
Yeah. The external feature is
Shaft.
connected with the bearing house. You
Bearing
can see
house.
the house, right?
It's
Yeah. Okay.
shaft and it's internal is
Yeah, they got two features, the external feature and the internal feature. So it's it has got two features. So yeah. So now let's talk about the size. In the actual machinery, sometimes the feet is loose, so the parts can move relatively. Yeah, it means there are some clearance. Yeah, it can rotate freely, such as when a shaft and hole fit together. If the feet is loose, they can move relatively. Otherwise, the feet is tight, and it can help ensure that they cannot move relatively. So the size of a shaft and a hole fit together determine the tightness. So here's the definition of the size. Size is a number expressing the numerical value of a linear dimension in particular unit. Usually we will use the unit of millimeter. Yeah. It's the most commonly used unit, millimeter. So when you join the mechanical in mechanical drawing, if you don't write the unit, it means the unit is millimeter. So it's in our mechanical precision design. So if you use the unit of millimeter, you can omit the unit when you write it down. Okay, when you write a number, if you didn't include the unit, it means the unit is millimeter. Okay, I'm sure you understand. So these two pictures just shows the size determine the feet is tight or loose. For this one, you can see the size of the shaft is smaller than the dimension of the hole, so their feet is loose, right? They can rotate relatively to each other. But for this one, the shaft is the dimension of the shaft is bigger than the dimension of the shaft hole. So their connection is tight. Their connection is tight. They cannot move relative to each other. And it means they cannot move relatively. Okay. The size determines the feet, right? So about size, we have some further terms. The first one is the actual size. Actual size. Actual size is obtained by measurement. By measurement. It means when you produce it, you use the different instruments to get the real size. So actual size just means that. And we should note that different places. For this one is a shaft. We look at it in two directions. Yeah. When we it's a cylindric. It's the button size. It's the button feature, and it's very just like this one. When we draw a cylindric, yeah, I'm sure you learned mechanical drawing. Yeah, you draw it like this, right? So when we use instruments to measure the size, we should know that we measure at different places, we will get different actual sizes. For this example, the theory cylinder, the actual size may be shown like in this feature. We measure here, they all get different values. And when we measure it, we use the dA to represent a whole actual size. We use the capital D, and we use a lowercase d to represent a shaft actual size. So we will use these two very often. So what this lowercase a mean? What do you think? We are talking about the actual size. So the A means actual. Yeah. So because we will use the capital D with a different footprint. Here we use A, it means actual size. So you need to remember this. And when we talking about the sizes, different. This is the symbol for whole actual size, and we will have different symbols for whole. When it associated with the whole, we always use a capital letter. It's the, for example here we use the capital D. The D is the size of the whole, and then we use the footprint to say it's the actual size of it's the actual size of the whole. Okay, and use the lowercase d to represent the shaft. When we use a lowercase, it's always associated with a shaft. Okay. So you need to, when we in a while when we talk about these two symbols, you should get to know what it means. Okay, you should know what it means. We just introduced the actual size. Now we introduce the second terms about the size is the nominal size. Nominal size is also called as the basic size. The basic size, it means the parts fit together. They have the same. when two parts fit together, they must have the same size. And the basic size is rounded after calculated from strength or stiffness according to material mechanics principle. And capital D is for a hole, and lowercase d is for a shaft. So nominal size or basic size is the size of when we design it. In our technical drawing, we always say, for example, when we design a cylinder like this, we need to assign this size. So this size is the basic size. So it's basic size. So for when we use a shaft to feed with the hole, they must have the same basic size. They must have the same basic size. And the basic size, how we get the basic size? The basic size is calculated according to material mechanics. It's the content in mechanical design. For example, you can calculate out the diameter. In this case, is 17.8. Is enough to support the force F. It's how to calculate it is in the material mechanics. And but when you fabricated the actual beam, you may choose 20 for the diameter. You can choose a value larger than the diameter you needed. Yeah. Because the value we always choose preferred values. That's why we learn in last course the preferred values. We always need to choose the values among the preferred values to fabricate the real beam. For two workpieces surface fit together, they must have the same basic size. For example, this hole is fit with this shaft, so their basic size must be the same. That's you need to know. That means the capital D equals to lowercase d. Yeah.
Only
So if we want to label the D here and here, so we label here, so we should use, if we label the D here, it should be it's capital D or the lowercase d. It's the capital D, right? Because it's a hole. So hole always associated with capital letter. Okay, so it's capital D. So for this, if you want to label here, it's lowercase d. Okay, it's about the nominal size or the basic size. It's the ideal size we want to manufacture it. Now let's talk about the limits of size. We all know that we cannot manufacture the exact size for workpiece sizes. To ensure their functions, we have to give the size limits. To confine the actual size at a certain range for qualified surface, we define the limits of size. Because if we give a basic size here, we cannot manufacture the exact size as we wanted. So we just set a limits for them. So now let's learn about the limits of size. The limits of size is the two extremely permissible sizes of feature between the actual size should lie. The limits of size being included. So we got maximum limit of size, and the minimum limit of size. The maximum limit of size is the greatest one, and the minimum limit of size is the smallest one. And we use this illustration to help you understand it. As we stated before, for both shaft and the hole, we all have the limits of size. So let's first look at the shaft. Okay, the shaft has so let's look at this line. So you think we just said the maximum limit of size and the minimum limit of size. So you think this line represents which limit of the size? This line. So first we shaft have a nominal size or basic size. We set here, but we set a tolerance for it. It can, as long as the actual size of the shaft is among this zone, we think it's okay. So we have these two lines. So what do you think? Which this line represents which limit of the size? We got two lines to represent the limit of the size. So this line represents what?
Shaft minimum.
It's the minimum limit of the size, right? Yeah. This one is the maximum limit of the size. It's very clear, okay? So this is for shaft. Also, for the hole, we also have these two lines, right?
Maximum and minimum.
Yeah, this one is minimum, right?
And this one is maximum.
Maximum. Okay. So this graph you need to understand. Okay. Understand. Okay. And we also have the symbol to represent the minimum limit and the maximum limit for both the hole and the shaft. So we use the max and the mean. The footprint is max and the mean. It represents for hole. It's the symbol for hole. Yeah, use the capital D. When we talk about the hole, the capital is always the letter is always capital. And for shaft, we also have the D max and the D mean. Remember, when it associated with the shaft, we use the lowercase d. So for shaft, we have the maximum limit of size for shaft. It's the minimum limit of size for shaft. It's lowercase d and the minimum. And as is printed here, the capital letter present is present for hole. Lowercase is present for shaft. The footnote is max or min. So when we manufacture a shaft or a hole, if we have these two limit values, so how we say it is okay according to our tolerance. So that's these equations. We just mentioned the capital D with the footprint A. It means what?
Capital D is
It's the actual size of the hole, right?
Yeah.
So the actual size of the hole is in this range. From the mean, capital D mean, to capital D max, right?
Yeah.
And for the shaft, it's the actual size of the shaft is in this range of lowercase d mean to lowercase d max. Okay, so as long when we manufacture a shaft or hole, we use instrument to measure the actual sizes. If the actual sizes is in the range of the two limits, the maximum limit and for minimum limit to maximum limit, we say okay, it fits our quality and it can be used. And That's the limit of the size. Next, we introduce the deviation. Before we introduce this, let's again to look at this graph. So when we manufacture real workpieces, for example, a cylinder with a diameter of 15. So we have to set the mean for shaft. We got to set the mean and the max, right? Yeah. The mean, the max, for example. Can you see it? It's normally the mean and the max we can calculate it. It's from 15 to 15.05. It's really a small range, right? So if we can draw a picture like this to illustrate the limits. But if we really use this graph, what problem will it cause, you think? Will it bring any trouble? We draw a picture like this. So if we use the real dimension to draw this picture, you will find that this zone is really tiny. Compared with it's the basic size, right? Compared with the size. So normally we do not draw a picture like this to illustrate the minimum limit and the maximum. We use deviation. Deviation, we propose the term is to simplify the standard table, and we use deviation to confine the size qualified. Deviation is termed as the algebraic difference value between a size and the corresponding basic size. Yeah. It's just we use the actual size to minus the basic size. We get the deviation value. The algebraic difference value means that there are positive and negative for deviation. When the deviation is positive, then we got the plus sign. And the plus sign cannot be omitted. For example, the plus 0.025 and the minus 0.012. So when we use a size we need to use a size to minus the basic size to get the deviation. So what do you think? We can use what size to minus the basic size? So to get a deviation, we need to use a size to minus the basic size. So which size we should use to minus the basic size, do you think? We have just introduced this one, right? This is what? Actual size. Actual size. We can use the actual size to minus the basic size to get a what? Actual deviation, right? Actual deviation. We also introduced the new D max maximum limit and the minimum limit. We can also use the maximum limit and the minimum limit to minus the basic sign to get what? Yeah, we can get the limit deviation, right? First, we use the actual size to minus the basic size. We get the actual deviation, and then we can use the limit of the size to minus the basic size to get limit deviations. So here we introduce the new symbols, EA. Okay. These two symbols EA is equals the actual size of a hole to minus the basic size, right? It's a basic size to get this actual deviation for this means the actual deviation for hole y because it uses capital E, right? Capital E. You can think this E is the short form of arrow, and the lowercase e a means the actual size of what shaft, right? Shaft. It equals to the actual size of the shaft to minus its basic size. Okay. I know there are many notations, and I hope you don't confuse me. So you guys understand? So when we talk later, we are if you don't remember, we will help you review it. Okay. Okay. So we just talk about we have the limit deviation. So normally we don't call it a limit deviation. We have two terms to specify to talk about it. The limit of a size minus the basic size, we can get two deviation. The first one is the upper deviation. Upper deviation is the maximum limit size minus the basic size. It's called the upper deviation. If you use the minimum limit size to minus the basic size, we get the lower deviation. So for a hole, we got its upper deviation and its lower deviation, right? Yeah. So and for a shaft, we also got its upper deviation and lower deviation. So here for hole, we got its upper deviation. It's his symbol, capital E and capital S. It equals to the maximum limit. So it's beginning, okay? In fact, in an hour ago, in the last hour, we mainly learned these symbols, and let's have a quick review. So we have the D, it means the size, right? So if it's a capital D, it means it's the size for the hole, and you use lower letter D to it's for the shaft. The footnote, if the footnote is A, it means the actual. So when we manufacture a hole or a shaft, we need it's the actual size of the hole in this range, the minimum size and the maximum size within the two limits. And if you use the size to minus the basic size, you get is the deviation representation. The actual deviation is in the range of the lower deviation to upper deviation. Okay, that's what we learned in the last hour. So let's move on. Then we introduce a new term called size tolerance. Size tolerance, it means the permissible variance range of qualified actual size. It gives the difficulty degree of manufacturing. It also represents the precision of the workpiece. It is the absolute value of the difference between the maximum limit of the size and the minimum limit of the size. For hole, we calculate using this equation. It's a maximum limit minus its minimum limit. We get TH. T means the tolerance. H, the footnote H, it means for hole. It's the tolerance for hole. Okay, we use this equation. In the same way, we can calculate the tolerance for shaft. Tolerance for shaft. This S means shaft. It is the maximum limit of the size to minus the minimum limit of the shaft. Okay. In fact, it is also equals to the absolute value of upper deviation minus lower deviation. So the TH also equals to capital ES minus capital EI. Okay. In fact, we can get this equation from this. We can add how can we get this equation from this? Yes, we can just TH equals to the max minus the min. So we can add a capital D here. We can minus capital D and add a capital D here. So, are they equal? We just minus D and here minus minus, so it's plus D. So this equation, they are the same, but the max limit minus the D, it equals to capital ES, right? It's the upper deviation. And we use the minimum limit of the size to minus the capital D, we get the EI, right? So these two forms of the equation, they are the same. They are the same. So the absolute value means that the tolerance is always positive. Because it's the absolute value. So the calculated result is always positive, and it will never be zero. It will never be zero. So, do you understand the meaning of these words? It gives the tolerance gives the difficulty degree of manufacturing. It also presents the precision of the workpiece. So, in fact, tolerance, the value, it can be calculated according to these two equations. So, if the tolerance, the value is very small, what it means? It means during the manufacturing, the workpiece must manufacture very precise, right? If the tolerance is very small, it means you have to manufacture it in a very small room. The tolerance is small. If the tolerance is small, then you have to manufacture it very precisely. So it increases the difficulty degree of manufacturing. And if the value is small, it also means that the precision of the workpiece is high. It's a high precision. It's with the high precision. So normally we will use the tolerance zoom. It's a graphical presentation to show the relationship between the tolerance and the deviation, and it can be presented. It can present the relationship of the feet between shaft and the hole as well. So this graph is very important. You really need to know how to draw this graph, and this graph can help you understand those relationship between feet, limits, and stuff like the notation we just learned. First, how we get the tolerance zone? First, we draw a line. This line means it's called the zero line. It's zero line. We need to write a zero at the left side. And above the zero line, we add a plus sign, and below it we write a minus sign. And we also draw a line perpendicular to this horizontal line and write the basic size here. Like maybe it's a 15 diameter shaft, so we need to write a 15 here. Then we draw a rectangular here to represent the tolerance for hole. And we need to write its upper deviation next to the upper line here, and write its lower deviation at the lower line here, And we also need to draw another rectangular to represent the shaft, to show the tolerance zoom of the shaft. We also need to write its upper deviation, lowercase es, and its lowercase ei here. The exact value should write here. And if you use the millimeter as the unit, you don't have to write the unit to indicate its unit. If you are using the unit of what do we say here? The micrometer. Okay, micrometer. If you use the micrometer, you need to indicate it here. Say you are using the micrometer. Okay. And we can. Normally we do not have to indicate its tolerance. The tolerance, because the tolerance can be calculated. It's just we use the upper deviation to minus the lower deviation, we can get the tolerance, right? Tolerance. If the tolerance is small, it means it's a component with a high precision, and it's difficult to manufacture. If the TH is large, it means it's with no precision and it's easier to manufacture. So here we introduce another term about the deviation. It's called the fundamental deviation. Fundamental deviation is the deviation near to the 0 line. We can, for example, for this hole, we know its upper deviation and its lower deviation. So which deviation is more close to the 0 line? It's the lower deviation, right? So in this case, for this hole, the fundamental deviation is the capital EI for this hole. And for this shaft, it has the upper deviation, its lower deviation. Which deviation is more close to 0 line? It's the upper deviation, right? So in this case, if we are talking about its fundamental deviation, it means it's the upper deviation. Yeah, okay. If the tolerance zoom overlap with the 0 line, then we should check which one is more close to the 0 line. Then that deviation is the fundamental deviation. So we can get 6 terms from the tolerance zoom for hole and the shaft. That is, first we got the D. We here use the example of a hole. So the capital D is what? It's the basic size, right? Basic size. And it got the upper deviation and the lower deviation. And we here got the tolerance for hole. And we have the maximum limit and the minimum limit. So can you figure out their relationship here? In fact, this graph can help you understand their relationship. For example, the ES minus EI, we can get the TH, right? And we use the maximum limit to minus the minimum limit. We can get the TH also, right? And how we get the EAs? The EAs is equal to D max minus D, and then EI equals to D minimum minus D, right? Right. In fact, their relationship can be illustrated by this figure. So we can the upper deviation minus lower deviation, we get TH. The maximum limit minus the minimum limit, we get the TH. The TH is the tolerance for hole. And ES plus D, plus D, or we can put the D in the right, it's the maximum limit minus D equals to ES as our definition, okay? And the lower deviation plus the basic size equals to the minimum limit of the size. So, in fact, according to this representation, as long if the basic size is always known, we will always tell you. And if we know 2 of the 5 values, we can calculate the rest of them. First, the basic size will always tell you. And if we tell you the upper deviation, and also tells you the minimum limit, you can calculate the rest of them, right? You can calculate the rest of them. So you need to figure out their relationship. So this is for the relationship for hole. So I want you guys to draw the same 2 pictures for shaft. Okay. So I will give you 3 minutes. You can try to practice it. Change the symbols. And this is called the tolerance zoom, the size tolerance zoom. You try to draw the picture for the shaft. Okay. Already know those concepts and how they are connected together. Okay. In fact, for shaft, I will show the tolerance zone here of the shaft. The shaft, you can use a rectangle. First, we need to draw the 0 line, and we use a line perpendicular to the 0 line and write the basic size. The basic size is here. It's a value. Right here, it's the basic size, and here we got the zone for shaft. You can write the shaft here to represent it's the tolerance zone for shaft, and it's the upper deviation is the lowercase ES, and its lower deviation is the lowercase EI, and you can also write its tolerance is this value. This value. You can use the lowercase ES to minus the EI to get the tolerance. It's the TS. T means the tolerance. S means the shaft. Okay. And that is how we draw the tolerance zone for shaft. And as for this relationship for shaft is simple. You just need to change the capital letter to lowercase letter. Yeah. And of course, this T do not have to change. You just change the H to S. Okay. So that's the relationship. That's their relationship. So now we can move on. So let's see an example. Given the basic size is 15 diameter, the hole has the maximum limit size is 50.025. The minimum limit size is just 15. And for shaft, the maximum limit size is this value, and the minimum limit size is this value. So try to draw out the tolerance zoom figure. You draw. This is the tolerance zoom of theoretical. Now you try to use the real values. Just substitute these symbols into real values. Okay. Just try to draw it. Okay. Anyone want to draw here? I think you can do it now. It's not difficult, right? So, but Anda try to draw here.
我是成功。
Oh, 成功. Oh, sorry. How about 成功? Try to give the answers of the exercise. Normally we just we draw a rectangle, but how the real length of the rectangle is associated with the real value also. For example, the EI is 0, so it must come to here. It's here, right? And you can calculate the tolerance. So then we can move on to the tolerance zone for hole and the shaft. Here, in this example, it gives us the maximum limit size and the minimum size for both the hole and the shaft. So we just use those limit values to minus the basic size. We can get the deviation values, both the upper limit, both the upper deviation and the lower deviation. So we got those deviation values, and we can find their zoom in this graph and indicate them. And so we can see here the lower deviation for hole is 0. So this line should align with this is the 0 line, not upper. Sometimes we should look into the real values here, and then for the upper deviation we can calculate the result is the 0.025. Remember to put the plus sign here. The plus sign should not be omitted, and we can get the tolerance zoom. And as for shaft, we can calculate the result too. The lower deviation is minus 0.041, and the upper deviation is minus 0.025, and we can draw its zoom. For more accurate drawing, you should also pay attention to see the rectangle you draw is correspond to the real values here. For example, the tolerance for hole, you can get the result is the 0.025, right? And for here, you can also get the tolerance for shaft. The tolerance is, you can use this value to make, you get what? This value, right? This is the TS. We also got this TH equals to So when you draw the zoom, tolerance zoom for hole and shaft, you need to also check if this value is bigger than this. So it's bigger than this one. So you can draw it more as more. The y is bigger than this value. Okay, to indicate the features. And also you should make those values in the same way. For example, this is
Yeah.
2.2. So the upper deviation, the corresponding line, the value, in fact, it should be here. If we determine the zoom for hole, then the shaft hole, it's the minus 0.025. So it should be well. So it should be this height. Hey, you can use it, and this starts here, right? And the shaft, the accurate drawing should be here, should be about here. So this is what you should be careful. But if you can draw like Chen Gong like this, it's okay. It's you get the 19% score. But if you can draw more accurately, then that's 100% perfect. Okay. Because the values are accurate. It's more accurate to indicate the tolerance zoom. So let's see the results. We can get those deviation easily, just minus the basic size and draw the horizon, the 0, 9, and put those 0 plus minus sign here, and indicate the basic size, and we got the hole, and we got the shaft, the tolerance of the shaft. And here it used the unit of micrometer. If you use the millimeter, you don't have to indicate the unit. You don't have to indicate it. Just like here. You can write the ES equal. Here also you can omit it. It's okay. Okay, that's how we draw the tolerance zoom graph. The graph of tolerance. So then let's talk about the feeds. Feeds is the relationship resulting from the difference value between the size of the features, the hole and the shaft, which are to be assembled. It refers to a bunch of workpieces before assembly, not for a certain pair of hole and the shaft. The feeds is referred to a batch of workpieces before assembly, not a certain pair of shaft, of hole and shaft. Then feeds have mainly includes two types. The first one is clearance. Clearance is the positive difference between the size of the hole and the shaft. It means that the hole size is larger than the shaft size. We use the capital X to represent it. We use the clearance. This is this fit type is the clearance. That means the hole size is bigger than the shaft size, and we can minus these two values to get the actual clearance, and we use X capital S to represent it. And next, another type is interference. Interference is the negative difference between the size of the hole and the shaft. It means that the hole size is smaller than the shaft. We use capital Y to represent it. So when we calculate its clearance and its interference, we use the same equation. For example, when we try to calculate the x equals to the size of the hole minus the size of the shaft, we get a clearance. So when we calculate the interference, we remember it's not to use the size of the shaft to minus the size of the hole. In fact, we use the same equation. For interference, we also use the size of the hole to minus the size of the shaft. It's a negative value, but it's okay. The negative value just indicates that the feet is interference. So, okay. So, no matter for clearance or interference, when we try to calculate the clearance or interference, we just use the size of the hole to minus the size of the shaft to get the clearance or interference. If you get the negative value, it means they are interference. The feet type is interference. So remember, always the hole size minus the shaft size. Then to look at it, if it is positive or negative. Positive, then the feet is clearance. Then if it is negative, it means that the type is interference. We can learn the classes of feet from the tolerance zone we just learned. Tolerance zone we just learned. For example, if the tolerance zone is drawn like this, so we can say what classes of the feet you think? The shaft is below, the tolerance zone is totally below the tolerance zone of the hole. So when they fit together, their feet type must be what? Clearance, right? Clearance. Because no matter the actual size is its actual size is in this zone for hole, and the actual size for shaft is in this zone. So we choose a value here to minus this value. It's always positive, right? It's always positive. So this is the clearance fit. It's a clearance fit. For the second, we keep the tolerance zone of hole here and move the shaft, the tolerance zone of the shaft from below it to up to it, from here to here. So when they fit together, which classes of the feet will be? Interference feet, right? It will be interference feet. So there are third condition. Yeah, they are overlap. They overlap together. So if we choose the hole here and the shaft here, you can get a clearance feet, right? If we choose the shaft, the value here and the hole value here, we get the interference feet. So in this condition, we call it the transition feet. The transition feet. So we got three classes of feet: clearance feet, interference feet, and transition feet.
Actually,
So in this case, it's the transition feet. Transition feet. So we remember the tolerance zone position relationship of the hole and the shaft, and we can grasp the three feet classes. This is our three feet classes, and there are two parameters: limit, clearance, and interference to describe every feet classes. First, we look into the clearance feet. From a batch of workpieces, any hole and any shaft fit together, there is always clearance. That means the size of any hole is larger than the size of any shaft. For example, here we can see the hole, the tolerance zone of the hole is always above the tolerance zone of the shaft. So we choose any hole from here to fit with any shaft from here. There's always clearance. So this class is called clearance fit. And the clearance value is in a range. For example, we can calculate the maximum clearance using the capital ES to minus the lowercase ei here, right? We can use value here to minus value here to get the maximum limit of the clearance, right? That's the maximum clearance. It's the maximum hole minus the minimum shaft. The biggest hole to minus the minimum shaft, we can get the maximum clearance. In fact, it can be calculated using the symbols we just learned. It's equals to the maximum size of the hole to minus the minimum size of the shaft, right? It also equals to the upper limit of the hole to minus the lower deviation. I just say it wrong. The upper deviation of the hole to minus the lower deviation of the shaft. You can get the maximum clearance. So in the same way, how we get the minimum clearance? We just indicate that this is the maximum clearance.
Actually, this is this and this. This one, for example, this one and this one. Is minimum.
Yeah, that's
This
correct.
one is minimum.
Yeah. So you just told me. Yeah, we just use the minimum size of the hole to minus the maximum size of the shaft. This indicates the minimum clearance, right? Minimum clearance. So we can get the minimum clearance like this. You use the minimum hole minus the maximum shaft, and it can be also calculated according to the equations. We use the minimum size of the hole to minus the maximum size of the shaft. We can get the minimum clearance. We can also get it by subtracting the capital EI and minus the lowercase es to get the minimum clearance. This is the clearance fit. And you can also calculate the variation of the clearance. The variation of the clearance is equals to the maximum clearance minus the minimum clearance. If we put the equation into this, we can find that it also equals to the tolerance of the hole for the hole and the plus the tolerance for the shaft. You can get the variation of the clearance. So this is about the clearance fit. Now let's move on to the interference fit. Interference fit is from a batch of workpiece, any hole and any shaft fit together. There is always interference. This means that the size of any hole is smaller than the size of any shaft. It means we can see from this figure, we can see that the zoom for the hole is always below the zoom, the tolerance zoom for shaft. You can see that. So this type is interference feet. So we can also calculate it's the maximum interference. So it's a maximum interference can be calculated by the minimum hole minus the maximum shaft. Just we use the minimum hole to minus the maximum shaft, we can get the maximum interference. It also you can also use this equation to calculate the maximum interference. And also we can calculate the minimum interference. Minimum interference, we can use the maximum hole to minus the minimum shaft, and it can also calculated by the following two equations. So, and the variation of the interference is equals to the maximum interference minus the minimum interference. You will find that the answer is also equals to the tolerance for the hole plus the tolerance for the shaft. That's the variation of the interference. And last, let's look into the transition feet. Transition feet is for a batch of workpiece. Any hole and any shaft fit together, there may be clearance or interference. It means when they fit together, there may be, it can be clearance. It also can be interference, because you can see there the tolerance zone for hole and shaft, they have certain area are overlapped area. So for transition feet, we can calculate the maximum clearance. The maximum clearance, the equation is the same as the clearance feet. Is the same as the clearance feet. We use the maximum hole to minus the minimum shaft, and we can get the maximum. Use the largest hole to minus the minimum shaft. We can get the maximum clearance. And for transition feet, we do not have the minimum clearance. We have the maximum interference. The maximum interference is using the minimum hole to minus the max shaft, and we can get the maximum interference. And this equation is equal to the interference feet, the calculation of maximum interference. And this equation indicates how to we can calculate the maximum interference. It's use the minimum size of the hole to minus the maximum size of the shaft, and we can get the maximum interference. And the variation of the clearance and interference equals to the maximum clearance and minus the maximum interference. It is also the same. It's equals to the tolerance for the hole plus the tolerance for the shaft, for the shaft. So it must be a little bit confusing now. Must be confusing. So in fact, but by illustrated by one or two examples, you will grab it. So now let's look at this example. Giving a pair of the hole and the shaft, the basic size is 15. The hole will give you the upper deviation, lower deviation. For shaft, we go to the upper deviation and the lower deviation. And I want you to calculate the maximum limiter size, minimum limiter size, the limit, clearance, interference, variation of a feet, and draw out the tolerance zone, and to find which class of the feet is. So, in fact, the key point is the tolerance zone. you have already learned it. So before you determine which class of the fit is, you should first try to draw out the tolerance zoom, and then you can calculate the related parameters. So I will give you 10 minutes and a break. Okay. So about 20 minutes later we will continue to it. So.
Thank you.
Got a question like this. We have got a trick to finish it. Anyway, we got to draw the tolerance zoom. So just draw the tolerance zoom first. Tolerance zoom. So here I have already drawn the tolerance zoom. For whole, according to the question, we got the upper deviation, the lower deviation. You can write here. Is that correct? Correct. Okay. And we got the shaft deviation for the shaft, the lower deviation, the upper deviation. Okay. So after we draw it, you can find that you can find the class of the feet directly, correct? Right? They are transition feet clearly. Why? Because this upper deviation is bigger than the lower deviation here. So we got a certain tolerance zoom overlapped. So we got overlapped. So it's the transition feet. So now let's also calculate the parameters one by one. The first is the maximum limit of size. Maximum limit size is we got to calculate this four value. This four values I believe is easy, right? Because the maximum size of the hole is equals to 15, and we just plus the ES, right? The ES we got here, so it's 15.025. That's the answer. And in the same way, we got the answer is the basic size plus the EI, right? We got the EI. EI is 0.12, so the answer is 15.012. We got here. In the same way, we can get the maximum limit size of the shaft and the minimum size of the shaft. Minimum size of the shaft in the same way. That's easy. So now we have answered the first to get the results of the first two parameters, and then move to the result. That's the limit of clearance. Limit of clearance. It's a little bit difficult than this one. In fact, it's not difficult at all. So in this case, what we got? We got the maximum clearance and the maximum interference. Do you remember? Yeah. For transition feet, we got maximum clearance and the maximum interference. How to calculate it? The maximum
X maximum is equal to ES minus EI.
X means the clearance, right? We got the maximum clearance. In fact, the calculation of maximum clearance is the same as the minimum interference. You will find out in your textbook. The calculation is the same. Their calculation is the same. The maximum interference is the same. The calculation is the same as the minimum interference. It equals to the ES to minus EI. Minus the EI. In fact, if you don't have to remember it. You just look at this picture. Why? It asks you to calculate the maximum clearance. So where is the maximum clearance? You can just see from this picture. You can find it. How to get the maximum clearance? We got the biggest hole and the minimum shaft, right? That's the capital ES minus lowercase EI, right? That's That's the calculation of the maximum clearance. And for maximum interference, how to calculate that? In fact, maximum interference, the equation is the same as the minimum in clearance. Here we need to calculate the maximum interference. How to calculate it? That is, we use the minimum hole to minus the maximum shaft to get the maximum interference, right? Yeah. That we can use the symbol. The symbol here is the EI minus the ES. Is that correct? So here I want to tell you is the maximum clearance, the calculation of maximum clearance is the same as the calculation of minimum interference. And the minimum clearance, the calculation of minimum clearance is the same as the calculation of the maximum of interference. They are the same. Okay. So we can get our answer here. The ES minus this value, what do we get? It's the point. So it's the 0.043, correct? And we can get our maximum interference by using this value to subtract this value. We get minus. Remember, there's a minus, and it's the 0.003. Okay, we got the answer here, minus 0.003. That's our maximum interference. Okay, so we got our answer here. This answer here. Then we come to this question: the variation of a feet. In fact, the variation of a feet you can calculate it in two ways. The first way may be more simple. It's you just find this tolerance. This is what? TH, right? The TH equals to 1.13. This is the TH. We can also get the TY, right? TY. TS equals to this value. Upper deviation minus the lower deviation, what do we got? We got this value, correct? So the variation of a feet is always equals to the tolerance of the hole plus the tolerance for shaft. So when we plus them together, what do we get? That's the point. I think there's something wrong. Oh, a mistake. This is 3, right? This is 3. Because this one minus this one got this. And so we plus these two values together, what do we got? We got this value. So 0.043 is the answer for the variation of feet. Because no matter what class of the feet is, no matter it's a clearance feet or interference feet or transition feet, it's always the variation of a feet is always equal to TH plus TS. And of course, you can also calculate it according to the equation here. Because, like we said, we use this equation to get the result. We can also get the answer by using the maximum clearance to minus the maximum interference. So we try to use this equation to get our TF. This is called TF. So this TF can also be using the maximum clearance to minus the maximum interference. So we use this value to minus this value, we get the same value, right? Because this is, it got a minus sign. It's a negative value. So we use this value to minus this value. We also get the same variation of the feet. Same variation of the feet. I hope you guys understand how to solve this kind of problem. It's one of the very important question. So this is the answer in the PowerPoint. You can see the results we get here are the same. The maximum interference, the maximum clearance, the maximum interference, and we can get the variation of the feet, and it's a transition feet. Okay. So, and the graph is first draw the 0, 9 and put the signs here and indicate the basic size and draw the tolerance zone for the hole. That's it. And the tolerance zone for the shaft. You can then get the result. So I think that there's something wrong with this picture, right?
Yeah.
It's not a 0. That one I draw is correct. So
No problem.
there's something wrong with this picture. It's,
Now it's good.
it's not starts from 0. It starts from this value.
0.0.
Okay. Okay.
That should be this.
Nice art.
So you guys understand how to
Yes.
figure this out. I hope I spent a lot of time explaining it. So I hope you guys at least understand it. Okay. Okay. Now you need to
Send it to them.
you can just I don't because there's something wrong. I can see if I can. I will send the picture to our. I think it's. Let's make it more correct. Okay. It's because just now that's wrong. There's something wrong with it. It's 12. Okay. Okay, so this is the correct answer, right? This is the correct. Check it. So this is the correct answer. Okay. So now let's move on to the section 2. I don't believe we can finish this section, but then let's introduce some parts. The second section is the standard of the limits and the fees. In the before, the size of the tolerance zone and the deviation, the fundamental deviation, are just random numbers. But in real production, those numbers cannot be random numbers. They must specify according to our ISO standards. So the section 2 is talking about how the ISO standards to use those limits and fixed values. And we got in this section we mainly learn to how to check the tables to find the deviation and the tolerance value according to the standard. First, we learned the standard tolerance grades. The standard tolerance grades are designated by the letters IT, followed by a number. You can look at your book, textbook. It's the table 2.4. Table 2.4. Look at your textbook, the table 2.4. it's the numerical values of the standard tolerance. There are 20 standard tolerance grades designated IT01, IT0, and IT1 to IT18 in the size range from 0 up to 3,000 millimeters. The size tolerance expresses the difficulty degree of manufacturing. It also presents the precision of the workpiece. The tolerance value is less. If tolerance value is less, the manufacturing is more difficult, and the precision is higher. If the grade number is smaller, the tolerance value is smaller, and the precision is higher. So you can look at your table 2.4. In fact, we need to know how to read this table. For this table, you got from IT1 to IT18. So, and in this column, you got the basic size. So we can see for different basic size and for different basic size, even we use the same tolerance grade. For example, the IT1, we can see if we change the basic size in different range, we can see the standard tolerance is changing. Can you see that? The standard tolerance, the value of the standard tolerance is increase or decrease along with the increase of basic size. Increase.
Yeah.
So why is that? Why? Because when the basic increases, if we want to maintain the standard tolerance, for example here, at 0.8, it will become more difficult. So when we say when we talk about a certain tolerance grade, for example, the IT1, it means for different basic size, it has a different tolerance. The tolerance is in fact, the concept of tolerance we have introduced. What is tolerance? Tolerance for shaft, that's the tolerance for shaft, and this is the tolerance for hole. So this value, this value, and this value is the tolerance, right? And this tolerance, the value of the tolerance is not randomly picked. It's not randomly picked. It picked according to ISO standards. That's why we here talk about the standards. So when we choose the standards according to the standard tolerance, we need to when it is specified certain tolerance grade, standard tolerance grade, we can find the exact tolerance value here. Using this table, we just find tolerance value, find out the tolerance value we needed. So here is a question. Which one is difficult to manufacture if you want to make a cylinder with a certain diameter? This one or this one? Then we can see they have the same upper and upper deviation, right? Upper and lower deviation. They have the same. So they are have the same difficulty, or this one has more difficulty.
Yeah.
This one has more difficulty. This one is more difficulty, right? In fact, why? So first, the deviation for these two cylinders are the same deviation, but as I just said, with the increase of a basic size for the same standard tolerance grade, it means it will increase along with the basic size, right? So, if we are making two cylinders with different basic size, this one is bigger. So, if they are in the same standard tolerance grade, if the nail grade is the same, which one has more which one is the position is higher? Which one? So which one has more position? This one or this one?
This one.
The bigger one, right?
Yeah,
Because I just said for the same standard tolerance grade. Yeah. This means if you manufacture a cylinder with a size of 10 and 15, for 10 the tolerance is just 1, and for 15 is 1.5. They are in the same standard tolerance grade. That means their position is the same. So if in this question this much larger basic size has the same upper and lower deviation, it means it has more precision. The precision is higher. Okay. So at the same tolerance grade, the manufacturing difficulty should be same. So the basic size is standard. Next comes the table 2.3. Table 2.3. Table 2.3 is the formulator for standard tolerance. This table is just to indicate that for the same precision, the tolerance value is associated with its size. The size is bigger, then the tolerance is bigger. Okay, but this is just like when we learned about the preferred values. There is a theoretical calculation, right? There is a theoretical calculation. We can just get the common ratio and calculate one by one. We can get the preferred value series. And here, we don't need to calculate the standard tolerance according to table 2.3. We just give you the results. The results is in table 2.4. Table 2.4. Table 2.4 is very important, and we are going to use it very often. Very often. The table 2.4 is the results of the table 2.3. Is the calculated results of the table 2.3. So the value, how to calculate it, you can calculate it by yourself. But you can, if you are interested with it, you can look up if you're interested in how to get the tolerance value, you can check the table 2.3. But normally we just look up the value according to the table 2.4. Table 2.4. So now let's have an example. Look at the tolerance value given basic size is 16 IT7 and the basic size 14 IT8. Just find the tolerance value according to table 2.3. Table 2.3. So try to find the tolerance value. Anyone find the answer? You need to find the tolerance value. So first I have to find it by myself first. Okay, it's 16. So what's the 16 can be used? 16 is to find the 16 is in the range of basic size. So you find the 16. The 16 is in the range of from 15 to 18, right? And the grade is IT7. So IT7 is what? You find what? 13. You find the 13, right? You find the 13. So that means for basic size 16, IT7, the tolerance is 13. So what about the next? The next.
25.
54.
Oh, different answers. Someone says 14.6 and someone says 15.4.
54, yeah.
So which one is correct?
Now she is 30 and 54.
So it is a little bit tricky now because why? Because I will use this PDF. So 18. So what we should use this range or this range? Which one? Or both of them are okay?
What is it?
Never both of is okay. There's always because you always choose one. Okay. So you should pay attention to this sign. It's bigger than this column and equal to this column. So 18 is equal to this value, right? So we still stick with this range, and we can. It's 8. IT 8. It's 46. It's 46. Okay. So you guys should now know how to find the standard time tolerance value if you are giving this condition. So I think today is okay now. Just that's all for today's class. Because next is the standard deviation. It's a little bit complicated. We will leave it to next lesson. And okay. But
next week is
content are not teach today. And I think let me check which question you can finish now. It's the I think these 4 questions you all can get answers. So this four answers. It's 2 weeks, and it's just keep practicing the new concepts and get the answers. So it's the exercise on your page 15.2, and from question 1 to 4, and there's maybe you have some problems with the symbols in the exercise 1. You can see the symbols. In fact, what is the symbol? The symbol you can ES and D lowercase e, D max, certain. Yeah. Just in the exercise 1, the symbol means you have to fill these symbols into the blank space. Okay. So for 2 weeks, finish it.
What are the different
You finish the question from these questions. Okay. These 4 questions. Finish it on your textbook. Okay. The next week, and I will first check your homework and help you correct your answers and continue with our standards of time tolerance and fits. Okay. So that's for today. Okay.